There are four important parameters in diffusion, bonding, and brazing, which must be controlled very closely in order to get the desired mechanical and microstructural properties at the joint interface. And these parameters include the four parameters of the diffusion, bonding, and the diffusion brazing. These are like the temperature under which the diffusion, bonding, or brazing is carried out. This is one. The time for which the high temperature exposure is being given, second. And the pressure to ensure the good metallic contact between the two components being joined is the third. And in some cases we may use the filler or the films for controlled alloying at the interface in order to achieve the desired objectives of lesser bonding time, good metallic contact between the two components being joined, reduce the diffusion time, because some of these alloying elements act as a diffusion accelerator also. So initially, if we talk about the diffusion, bonding temperature, the diffusion bonding temperature is the most important parameter in the diffusion bonding, because it affects the two things very significantly. One is the diffusion rate or diffusivity or diffusion coefficient, and the second is the mechanical properties like yield strength and percentage elongation. In addition to this, the metallurgical properties like the phase transformation, the recrystallization, all those are also affected by the temperature. So now basically the diffusion bonding temperature directly governs the mechanisms dictating all the aspects influencing the development of the bonding or the joint through the diffusion bonding approach. So if we see how this the diffusion bonding and coefficient how this diffusion bonding rate and diffusion rate, so the diffusivity or the diffusion coefficient is significantly dictated by the temperature. So here if we try to understand the relationship between the diffusion coefficient which is being influenced by the temperature, then relationship is like this: D is equal to D naught. D is the diffusion coefficient at a given temperature in Kelvin. So then D naught is a coefficient or the constant proportionality constant e raised to the power minus q by RT. So here Q is the activation energy for diffusion, T is the absolute temperature, and the K is the Boltzmann constant. The diffusion bonding is usually carried out above the recrystallization temperature, say somewhere at about 0.5 times of the melting point, where Tm is the melting temperature of the base metal or the parent metals in Kelvin. For many metals, the diffusion bonding is also carried out over a wider range of the temperature on the higher side, starting from the say 0.6 to 0.8 times of the melting point temperature in Kelvin. Okay, in any case, depending upon the pressure allowed, the time in which the diffusion bonding is to be realized, the surface preparation or surface condition of the bonding, then the temperature must be established accordingly, so that the sound and good metallurgical joint can be developed. So indirectly, the optimization of while establishing the diffusion bonding temperature, we must consider the pressure being used, diffusion bonding time, and surface condition, apart from the like filler metal or the interlayer, if anything like this is being used. Another important factor in diffusion bonding is the time, and the time of the diffusion, the time for which diffusion bonding is to be carried out, significantly dictated by the temperature at which the diffusion bonding is being performed. Okay, because it directly affects the rate at which the various reactions which will be taking place at the interface. Okay, so if see this is these are the two components, and here the diffusion will be taking place in order to develop the metallurgical bond. Then the distance up to which the diffusion will be occurring across the interface, that will be dictating the extent of the metallurgical changes or homogeneity across the interface. Say from the interface up to the distance x, if the diffusion has to occur, we can say as a diffusion length is say x. That is the average distance traveled by the migrating atoms by the during the diffusion. So if the diffusion length, that is the distance being traveled by the atoms during the diffusion at a given temperature, if that has to be expressed, then how to relate it with the diffusion temperature or diffusion bonding temperature. So the diffusion length, that is the average distance being traveled by the atoms at a given temperature T. Then we can write a relation like this: x is the diffusion length equal to c, that is the constant, d into t. D is the capital D is the diffusion coefficient at temperature T, and at a given temperature, that is T, and the small t, so this is the diffusion bonding time. This is the diffusion coefficient. This is the C is the constant. So diffusion coefficient at temperature capital T at a given absolute temperature of the diffusion bonding, what will be the diffusion length? So if we see this simple equation, this average diffusion length is found proportional to the square of the diffusion bonding time. So if we see here, diffusion coefficient is found proportional to the or you can say varies exponentially with the temperature, while the diffusion length is being proportional to the square root of the diffusion time. So the diffusion based reactions progress with the square root of the time, whereas these reactions will be progressing exponentially with the temperature as a function of temperature. So basically the diffusion based reactions, they change is proportional to the square root of the time, and this variation is like say exponentially as a function of temperature. So these two things will bring in the significant change, and this also speaks this relationship speaks about the relative influence of the diffusion temperature and the diffusion bonding time. So since the diffusion based reactions change exponentially with the diffusion bonding temperature, while the diffusion based reactions are affected as a square root of the time. So the more significant effect of the diffusion bonding temperature as compared to the diffusion bonding time. Okay, so it is very crucial to control the diffusion bonding temperature, while effect of the diffusion bonding time is somewhat less. It has been observed that the diffusion, like the kind of the metallurgical bonding affecting the joint strength as a function of the diffusion bonding time and pressure. So both will be affecting the joint strength. Okay. In general, this relationship is found like this, where we have the diffusion bonding time or diffusion bonding pressure, and on the other hand we have the joint strength. So initially the diffusion bonding time joint strength increases, and then it gets stabilized. Okay, so this is the stage when we find that the metallurgical joint has been complete, and the initial stages there will be reducing proportion initial stage with the increasing value of the diffusion bonding time and the diffusion bonding pressure. uh, with the increase of these two parameters, there will be reducing the situation of reducing voids at the interface, and when these voids are completely eliminated, we find that uh, the curve gets flattened and there will not be any further increase in the joint strength with the increase of the diffusion bonding time and the bonding pressure, which and the same is true for the recrystallization also. Like whatever the recrystallization has to happen, that will be completed in a certain period of time during the diffusion bonding, and thereafter no further change in the microstructure in terms of the recrystallization will be taking place. Actually, the diffusion bonding time varies significantly. It can change from few minutes to the few hours. Like say you may get a diffusion bond in 5 minutes also, or it may take like say 3 to 4 hours also. It depends on the number of parameters. Okay, and this is primarily limited due to the, like say, the mechanical and the thermal inertia associated with the diffusion bonding system, like say the vacuum hot press or the diffusion bonding system which is being used. Okay, so whenever we try to change the temperature because of this mechanical and thermal inertia, whenever we try to change the temperature or the pressure to a given level, these two things do not happen instantly. Not these things, this change do not happen, these changes do not happen instantly, rather it takes long to get affected. Like say if you want a temperature of 600 degrees centigrade, so it may take a long time, like say it may take like 2 hours initially to reach, or 1 hour depending upon the heating rate and the system capabilities. Likewise, if you want to apply the pressure and you want to control the pressure within certain limit, the system will take some time to reach the desired loading in order to achieve the desired pressure. So like say it always takes some time to reach the set temperature and set pressure. So this time required to reach the desired values is simply added, and if we subtract this time, like say if assuming that there is no thermal and mechanical inertia, then we can find that the welding time or diffusion bonding time may be very short. Like it may be as small as like say it is very less, even less than 1 minute or so, to facilitate the diffusion bond if it can be realized. If the change in pressure and temperature is instant, then it can be very short. Okay, so this so apart from the diffusion bonding temperature, which is significantly affecting the diffusion bonding coefficient, so that the average diffusion length x being affected by the diffusion bonding time and the temperature, and in order to develop the sound and reasonably good metallurgical bonding and the desired strength, it is important that sufficient diffusion bonding time is allowed. But in diffusion bonding it takes very long to develop the uh, metallurgical bond. So long diffusion bonding time is contributed by the mechanical and thermal inertia of the system which is being used. Okay, the second is like the kind of the diffusion coefficient for a given temperature, and third is the like surface preparation, how good surface the preparation is carried out, which is in terms of like say the straightness, flatness, and certainly the smoothness, that is the RA. So if the surfaces are perfectly straight, flat, and of the low RA value, so initially, even in the initial stages, there will be good metal to metal contact to facilitate the diffusion bond. So the number of voids even from the beginning they will be less. Another important the parameter of the diffusion bonding is the pressure. This is very difficult to deal with because another important parameter is the pressure, but it is difficult to control as compared with the temperature and the diffusion bonding time, because the temperature, diffusion bonding temperature, and the time can be closely controlled, while the control over the pressure is a little difficult. There will be number of aspects related with this. So when during the diffusion bonding, when pressure is applied, okay, so the interfacial asperities, peaks and valleys present here and there, they will get collapsed. So this collapsing will be leading to the surfacial deformation. So this superficial deformation will be leading to the increased metallic contact. At the same time, we will notice when the superficial deformation is taking place, it will be reducing the, due to the deformation, it will be reducing the recrystallization temperature, and it will be forming the number of increased number of the diffusion channels. So diffusion is facilitated, the recrystallization temperature is lowered, so and the metallic contact between the two components being joined, that is increased. So these are the three things being affected by the temperature. So increasing pressure in any case helps in improving the diffusion bond formation. Okay, so it is in general, if we notice, increasing pressure in general increases the pressure joint strength up to a limit, and thereafter it gets stabilized. Okay, however, the maximum magnitude of the pressure that can be applied, it depends on the system capability. That is one. The second is the component geometry itself, because it is possible that the component may not be able to handle or sustain the high pressures. And the third is the kind of the joint which is being made, whether it is the similar metal joint or the dissimilar metal joint. The situation is more complex in case of the dissimilar metal joint, because there is a possibility like one metal is having 600 MPa strength, one component is having 600 MPa strength, another is just like say 300 MPa strength. So if you choose the pressure greater than the 300 MPa, then bulging may start, upsetting of the low strength metal may start, and you may lose the geometry of the component under the high pressure. So it is to be kept in mind, like whatever the pressure is being applied, that is less than the yield strength of the metal. Otherwise, see, the bulging and the deformation of the component can take place. While the too high pressure cannot be applied many times due to the system capability. So for developing the diffusion bond of very large size components, we need to apply really the desired minimum pressure, and that cannot be applied because of the system capabilities. Okay, system, you may not have those very high capacity presses to induce the desired pressure. And another aspect is when we go for very high pressures, the system cost becomes high, and it needs much better control, and it involves the more complex procedures for developing the diffusion bonding using the high pressures. Okay, so that makes the process little unpopular. Okay, so you have seen that the pressure to be applied it depends on the metal system to be joined, the surface condition in which the joint is to be made. Rougher the surface, greater will be the pressure requirement, so that the good metallic contact between the two can be established. Likewise, higher the strength, lower the ductility, greater will be the pressures that will be required at the diffusion bonding temperature. So we must consider the kind of pressure to be applied will be influenced by the surface condition and the yield strength of the metal at the diffusion bonding temperature. Then another important aspect in diffusion bonding is the kind of the metallurgical changes which will be taking place. Changes during the diffusion bonding. So basically there are two types of the metallurgical changes which are of the great importance, that is like the phase transformation. This is one. A phase transformation may occur in form of, like say, the change in crystal structure, say from BCC to FCC or FCC to BCT, like that's what typically we get in case of the iron. So the metals like iron based systems, then the cobalt, then titanium and zirconium, so these systems show the allotropic behavior. The phase transformation take place in these metals. Okay, and in some of the metals, in presence of certain alloying elements, tends to form certain specific kind of the phases. Okay, so the change of phase is one thing, and the formation of phase is another. Like the phase formation, so like we will notice like certain kind of the phases are favorable from the diffusion point of view, while other kind of the phases are unfavorable. So the phase transfer, the kind of phase or the type of phase being formed, that affects the diffusion and the, like say, the melting tendency at the interface and the strength of the joint. Like the formation of the poor phases reduces the joint strength, like unexpected melting of the low melting point constituents being formed at the interface also reduces the joint strength, and the time being taken to develop the good metallurgical joint is being affected by the diffusion, and which in turn depends on the type of phase being formed. So as far as the phase transformation is concerned, phase transformation affects the two things. Like during the phase transformation, metal tends to behave like more plastic. Okay, this happens during the phase transformation. Similarly, during the phase transformation, the diffusion is also enhanced. So both these things are actually favorable. Like say, if when the phase transformation is taking place, like as I said, in case of the cobalt or iron or titanium or zirconium, whenever in the diffusion bonding conditions of the temperature, the phase transformation is taking place, the metal during the phase transformation, metal tends to behave in more plastic way, and if that is the case, then it will be facilitating the yielding at the interface. So surface layer deformation will be leading to the more metallic intimacy, and that in turn will be leading to the improved the diffusion across the interface, which is important. Similarly, this kind of the phase transformation also can be observed in terms of the recrystallization. Okay, so not just the allotrophic phase transformation, but the recrystallization also leads to the situation where metal tends to behave during the phase transformation in more plastic manner, and the diffusion coefficient is enhanced. So both these are helpful in facilitating the diffusion bonding. The improved plastic behavior is facilitating the increased the metallic intimacy across the interface or at the interface, and increase the diffusion bonding, increase the diffusion coefficient will be leading to the faster diffusion across the interface, and so the diffusion bond formation. Okay, sometimes introducing the certain elements, like introduction or the presence of certain elements at the interface, at the diffusion bonding temperature, this leads to the formation of the certain kind of the compounds. Say at the interface we have added certain kind of the film. Okay, certain kind of the elements have been introduced. These can be introduced in different forms, like it can be in form of films or foil, okay, in form of powder or in form of coatings. Okay, if these are present, so these presence of these alloying elements sometimes is ensured intentionally to realize the certain objectives. Like some of the elements act as a diffusion accelerator. So when these diffusion accelerators are are present at the interface, these accelerate the diffusion of the base metal into the film, or the diffusion of atoms from the film into the base metal, and it is ensured that after the diffusion bonding all this film gets diffused uniformly in the base metal. So there is no concentration gradient. Say initially the concentration gradient may be like this, okay, very high presence of that particular element which is present at the interface, and after the diffusion bonding you may notice like the concentration gradient has reduced significantly. Okay, so it is desired that these diffusion accelerator will be facilitating the diffusion across the interface, and that in turn will be reducing the diffusion bonding time. These diffusion accelerators, due to the improved diffusion, helps to reduce the reduce the voids. That's what you can say, the volume diffusion of voids present at the interface is facilitated by this diffusion. Okay, but if and another important thing, these diffusion accelerators, these must get dissolved in the base metal, and if these are not getting dissolved, then you will find that these are leading to the formation of some kind of the phase compound, and presence of these phases may be, or compounds may be, of the low melting point. This is one. These can be hard and brittle, so leading to the partial melting. So all these undesirable things can be there if the diffusion accelerators are not dissolving and distributing getting homogenized near the interface properly, and these are left, or these are not or these are forming some kind of the phases, intermetallic compounds, leading to the undesirable effects of these phases in form of low melting point, hard and brittle, and the partial melting. So these can be especially the problematic for the joint performance. Okay, so it is very important that these diffusion accelerators are selected appropriately, or the desired diffusion activators or accelerators are to be added at the interface are selected properly. Another purpose of using these films and foils is that since these are selected in such a way that these are soft, these are thin. Okay, so when these are present at the interface under the diffusion bonding temperature and pressure conditions, these will get yield, and these will be filling the gaps, voids, to improve the metallic bonding across the interface. So even if the surface is initially rough, when these films and foils are added, these and in the diffusion bonding temperature and pressure conditions, these will get yield and fill up the gaps. Like if this is the surface is proteins, then films may fill up like this. Okay, so this kind of the filling will improve the metallic bonding between the two components being joined. And considering these aspects, if we choose the diffusion accelerators or films and foils to be used for the diffusion bonding, these can be extremely useful. So when the filler metal is selected appropriately, it can be useful in number of ways. okay, because it helps in the diffusion bonding temperature. So this is good if you can realize the diffusion bond at the lower temperature. It reduces the diffusion bonding pressure. So this is also good. You can, for a given press size, you can develop the diffusion bond of the larger size components. It also reduces the diffusion bonding time. So all these three things are favorable, and this time reduction is also attributed to the, so you can say, increased metallic contact is one between the components to be joined, and the second is the increased diffusivity. Okay, so it increases the diffusivity, you can say, because it acts as a diffusion accelerator, and sometimes it also helps in cleaning through the scavenging effect of the undesirable elements. Scavenging effect of the undesirable elements. So these are the like some of the purposes which are realized when a very suitable filler metal is selected. And these filler metals, as I said, can be in form of powders, coatings, or films and foils. So if the coating is to be developed, usually, like say, the electroplating is one of the method, sputtering is the another method, or condensing the element onto the surface. And usually these are thin. Actually, this thickness is less than the 0.25 mm, or that you can say less than the 250 micrometer. It is always preferred that these are thinner ones. Just as an example, like say, the beryllium is added at the interface when developing the diffusion bond of the nickel alloy. So this beryllium acts as a diffusion accelerator, which in turn helps in reducing the diffusion bonding time. At the same time, these diffusion accelerators should not help in forming the very low melting point constituents, so, which will be melting at the interface by forming, like say, the low melting point eutectic at the interface. So it is important that the filler metal is chosen very carefully. So if that is not done, we can say improper the filler selection can lead to the, like say, reduction in the decreased joint strength, okay, reduced high temperature stability, because system or joint interface may get partially melted or weakened significantly due to the formation of the undesirable constituents. It can form, like say, the metallurgical degradation. Undesirable metallurgical changes can take place, and sometimes even this can promote the corrosion. So the corrosion issues can also be promoted by the improperly selected filler metal for the interface. So that's all from my side. Thank you for your attention.